Okay, so we're going to start our discussion on low-pass filters here, and um, remembering where we were at before here, um, that we had kind of gone through and seen why we determine the minus 3 dB point to be where we determine, quote, or define what the cutoff frequency is, and that's because it actually corresponds to the signal being at half power. And really power is what we're interested in. So let's look at a very simple low-pass filter to start with, and we're going to analyze this both just on a kind of very high level, just well, this has to be a low-pass filter, to diving into the equations, and actually not just diving into the equations, but actually figuring out what the cutoff frequency is. So we're going to look at a very simple circuit. And this is just a simple RC circuit. And this is my V in, and then my V out is going to be across the capacitor. Now, I'm claiming this is a low-pass filter, and we should kind of think about this, why this would be a low-pass filter. At low frequencies, we said that the capacitor behaves as an open circuit, and so if you're thinking of it behaving as an open circuit, the voltage you'd be measuring would be simply the input voltage. But then at high frequencies, this capacitor acts as a short, and if you think of acting as a short, I'm just going to draw on a line here. A short here, well, what's the voltage drop across the short? 0. So at high frequencies, there's no output voltage. So low frequencies get passed, high frequencies don't. So that's kind of the, kind of looking at it from a big picture. And again, you can always figure those things out by remembering here that just kind of keeping in your head that the impedance of a capacitor is minus J over omega C. That's how I do those quick kind of like, well, how do I know this two circuit component circuit that we're looking at here is a low pass filter? Because just looking at the impedance of a capacitor with respect to frequency. Alright, but now let's dive in and actually get into the equations here. So whenever we're going to do these here, well, since the cutoff frequency, we want to know what is the cutoff frequency in terms of circuit components. That's our ultimate goal for this video here, is determining the circuit components that, like, how we can determine the cutoff frequency based off the circuit components. Now, some of you might already say, oh, I know what the answer is, because it is a pretty simple answer. But we're going to go through and do all of the derivations for it here. So how are we going to do that? Well, we're going to find my transfer function. And this is a fairly simple one. If I do a Laplace transform, I get 1 over SC and R, and I'm just going to do simple voltage division. So I have 1 over S times C over R plus 1 over S times C. Now, you might think I'm going to multiply through everything by S times C, and I'll go ahead and do that. I wouldn't, but that's just because I know where I'm going to in the end here. And depending on what you're doing, sometimes you would multiply this by S times C, but we'll get to in a minute why I'm not going to want to write my answer like that. Okay, so then we get here where this is just 1 over S times RC plus 1. Pretty straightforward. But remember, what do we typically want? The reason I say, oh, maybe we don't want to do that, is that we want a 1 in front of S. So I'm just going to go ahead and factor out an RC. And if I factor out an RC, I'd have 1 over RC times S plus 1 over RC, which does just become 1 over RC, and I'm writing it in a weird way, but you'll see why in a little bit, why I'm writing it like this. S plus 1 over RC. Okay, so this is my transfer function, h at s. Well, I want to look at, I'm going to need, in order to determine what my cutoff frequency is, I'm going to have to know what the magnitude of h at j omega is. So I'm first going to just look at h at j omega. So all I do for that is just plug in 1 over RC, and then I have j omega plus 1 over RC. Now let's just remind us, because I'm really wanting to look at the magnitude of h at j omega, because that's my definition for cutoff frequency. Let me scroll back up here. Remember my definition for cutoff frequency. So I'm going to need the magnitude of it. Well, the magnitude is just, you can think of it, quote, as absolute value, but it's not. You have to be careful with complex numbers. So I'm going to write this off. If we have, how do I want to put this here? Just trying to not use any. If I have D is equal to A plus JB, the magnitude of D is then simply the square root of a squared plus b squared. And again, the reason for this is literally, if you look at it as plotting that complex number, real, imaginary, this would be A, this would be B. So you're literally doing Pythagorean's theorem here. So now the nice thing is for the numerator that is pretty easy, because the numerator I only have a real part, so I'd square that real part plus 0 squared, and then I'd do the square root of it, so the numerator still stays as 1 over RC. But the denominator becomes the square root of omega squared plus 1 over RC quantity squared. Alright, so that's h at j omega. Now, I scrolled up to here that my definition for h at j omega c is equal to 1/2 h max. Now, the good thing for us is, let's think about when this thing would be a maximum. I mean, we can just look at this h at j omega here. So let's just look, I'm going to circle it here. We're just going to look at this here. When would that be a maximum? Well, don't overthink it here. R and C are fixed values in the circuit. The only thing that's changing here is frequency, omega. And omega can go from 0 up to infinity. Well, the bigger omega gets, if this becomes big, well, the denominator is going to get bigger, which is going to make this smaller. So if this was 0, that would make this the biggest it can possibly be. And so if omega was 0, gives h max, and so that would just mean that h max is equal to 1 over RC divided by the square root of 1 over RC squared, which we can quickly see is just 1. So what does that mean here? Well, we need to find out, I'm going to plug in here, I want to know I have 1 over RC, and now I'm going to say, well, I'm going to plug in the corner frequency, So I have omega c squared plus 1 over RC squared, and that's going to have to equal 1/2 times 1. Okay, now this looks like this is going to be horrible. It's really not going to be as bad as you think. Let's just do some basic mathematics here. So I have 2 over RC is going to be equal to the square root of omega c squared plus 1 over RC quantity squared. Square both sides. Did I do that correctly here? Something seems wrong to me a second. Let me think for a second. And the issue I had is that this is, you probably all caught it. I was like, something's not right here. And it's because it's not 1/2. It's the 1 over the square root of 2. It's 1/2 when we deal with power. So I've got square root of 2 there. Okay, that makes everything work now. Now we're going to square both sides. So we've got 2 over RC squared is equal to omega c squared plus 1 over RC. Well, and I'm just going to write this as 1 over RC squared because clearly 1 squared is just 1. But now, honestly, this is not hard to solve because what would I end up getting? I get omega c squared is equal to 1 over RC squared. Just subtracting it. And then omega c, technically it's positive and negative, but we know we don't have the negative frequency, so it's just positive. Taking square root of both sides, we get omega c is just simply 1 over RC. Now, what's important to think about this here is there's something actually very useful about this. Let's go back to the transfer function. H at s was equal to 1 over RC over s plus 1 over RC. Now, what I'm going to do here is I want you to see something here. Notice here. That's not coincidence. So in other words, for my low-pass filter, we have H at s equals omega c over s plus omega c. So we have that the number sitting here in the numerator and the pole here. So the pole gives me the cutoff frequency. Now the other thing to remember here is this is of course in radians per second, is what omega c is, which we'll look at a couple examples here in a second in another lesson. But what I really want to wind up with is that any circuit that has a transfer function of H at s equals, and I'm going to write A over S plus A, is a low-pass filter with cutoff frequency omega C equaling A. Now that's going to be important when we look at our next circuit in the next video.